Hey, I'm Shri, and for the past few weeks, I've been working on building an AI algorithm that can detect lanes and cars when driving. Computer vision is all around us. We use it when we try to log into our iPhone using face recognition, to even detecting cancers and other diseases, and even all the way to autonomous vehicles. Self-driving cars are going to completely change the way we humans transport and move all around the world. Using sensors and technologies such as LiDAR, radar, and cameras, we're able to create a system that can drive by its own while also driving better than a human. Object detection and lane detection both play an integral role in terms of figuring out where cars are and especially lane lines, so we don't drive over them or we don't run into other pedestrians or cars. This project uses a pipeline that's extremely robust and faster than current deep learning alternatives out there. Okay, that's enough. Let's just get right into the lane detection pipelines and the object detection pipelines. When we first get our image from the self-driving car, you notice that there's a lot of noise in the image. And basically what that means is the fact that the images generally come in an RGB format, red, green, and blue. And the problem with that is the fact that we don't necessarily need RGB. Because the fact that this not only does increase compute, but increases noise in the sense that we add trees obviously, and other buildings that aren't really relevant to the detection pipeline. So what we can do is, if we were able to extract all this noise and choose a different color scale instead of RGB, we can completely compress the image and be able to process it in a more computationally efficient way. So the first thing we can do is simply convert our images to grayscale. The best way we can approach this problem of converting to grayscale is by using an approach known as the Solvable Filter. And basically what this means is that this algorithm uses a 3x3 kernel, which you can think of as a small rectangle that kind of scans across the images. And what happens is that these kernels have values in them. So for each pixel, if it was a 3x3 grid, it would have 9 values. And what happens is, as that kernel scans across the image, it takes the dot product of its multiplication. So for the 3x3 matrix that occurs from the kernel and for the actual image, both of them multiply together and we take the dot product. And that's kind of where we get something known as a convolution. We are now able to desize the image and make it a lot smaller while retaining the same amount of information. From there, we take the gradient of the derivatives, and that resulting convolution that occurs allows us to successfully extract the features from the image. And we top this off by simply taking the magnitude of the gradients and threshold the binary image. So this is how it will look. Now that we've done this for the lane detection pipeline, we can now do a perspective warp and get a bird's eye view of the lane itself. And what this will allow us to do is get rid of all the trees and the buildings and other cars in the background, because that isn't necessarily relevant to our lane detection pipeline. From there, we'd create a specific region of interest where we'd want to successfully warp the image and get the bird's eye view. So given this bird's eye view image, we can now use a polynomial trajectory algorithm, which is basically like a quadratic formula. And using that, we're able to now take the curved lines of the lane. So for example, for our image where we had these white pixels, we now fit them against a polynomial trajectory algorithm, which will now give us the resulting coefficients of a quadratic formula, therefore giving us the actual curves for the lane. Yeah. And now that we've built the lane detection pipeline, let's now move into actually detecting the cars in our image. The way we can actually do the object detection pipeline is through using an algorithm known as a support vector machine. And what the high-level goal of this SVM, otherwise known as a support vector machine, is to create a linear hyperplane to maximize the distances between two sets of data. So in our case, what we can do is we can bin the histogram values of images that are a car and images that are not a car into a discrete number of bins. So in example for this project, I chose to bin the histogram values into 8 bins specifically. So from there, what we can do is, now that we've classified those two sets of data, we can now fit this into the algorithm and help get discrete differences between a car and an image that isn't a car. One thing to really note here is the fact that because of the fact that we've already binned our histogram values into these discrete set of bins, we can actually take the histogram of gradients. And what this basically means is, say if that had like a white pixel and then a black pixel, the derivative or the rate of change between those two pixels would be substantially high. And what this means is that if the derivative was 1 as an example, now that pixel could be 1. And if I had a different change where I had 2 black pixels, right, and the derivative was 0 because of the fact that the pixels are the same, I'd have a 0th pixel. So now what this basically means is that I can kind of, in a sense, take the outline of a car and kind of see what is the car and what's its outline. And using that facial and spatial information, we're now able to pass this into the SVM model, which actually returns an accuracy of more than 99%. Now that we've really fed this into the SVM, we now need to perform a sliding window implementation. And what this basically means is that we, just like in the case of kernels and the Solvable Filter back in the lane detection slide, we'd have sliding windows which would scan the image, and wherever there's a car, we could plot that on a heat map. So say if certain pixels where this rectangle was recognized as a car, then we could put that onto a heat map. And now we would actually group the resulting heat map. So if I had like a pretty big heat map output for every single place where there is some sort of heat where the car is detected, now I can kind of group them to be able to get proper bounding boxes and get the actual car detection pipeline up and working. And yeah, now we can pair the lane detection pipeline and now the object detection pipeline and get the final output.
But I can't.
And yeah, thanks so much for watching. Just as a quick side note, I've also played around with the development of really fast and rapid deep learning tools such as mobile SSD as a popular alternative for object detection in real time. And I've played around with this, and what I've kind of noticed is the fact that it does really well with the dense environment. So in this case of this lane detection object detection pipeline, you can notice that it's really good in spatial environments where there's not many cars and it's more of a highway situation. But what you've noticed with the mobile net SSD is the fact that this works a lot more in dense and more dynamic environments where there's a lot more cars to detect in cities and extremely packed roads. And yeah, if you have any questions, feedback, comments, feel free to give me a message on the social media link in the description. And feel free to take a look at the code in the GitHub below. See you in the next video.